Hello everyone, so welcome to my channel. So in this video, we will continue our introduction about linear regression and correlation. In our last video, we already talked about what is an empirical model and some important terminology in the linear regression. So in this video, we will continue about how we can construct the empirical model. This means how we can decide the two parameters, the beta 0 and beta 1 in our empirical model. So as we said, this is different with the previous statistical inference, which means we have some information about our sample and we try to use information of the sample to get the information of our population. Here, what we work on is we have two variables here, x and y. For these two random variables, x and y, so they will have some relationship. So here we work on the linear relationship, and we try to find this relationship based on the data we have. So here the first thing is assume we have n pairs of the observations. So we denote this by xi and yi. And then what we have is, because this xi and yi is about the data observation, or we say the sample of our x and y. So we have this pair of observation also have the linear relationship. So we can rewrite this as this equation. Yi is equal our beta 0 plus beta 1 xi plus ei. So here the ei is a residual of our data. Whenever we have a pair of the observation, we can compute this ei for our model. And here this ei is very similar to the error term in our empirical model. Then how we can decide the beta 0 and beta 1? So we know this model is a linear relationship, right? So if we draw the graph of this equation, this should be a line. So what we want is we want to decide the beta 0 and beta 1, which is best fit our observation. Or in other words, if we draw a graph about our data xi and yi, then, for example, we have this the horizontal one is our x-axis, and then the vertical one is our y-axis. So here we can use the star to denote all of our observation. So, for example, we have one data here by the x1 and y1 data we have. Or maybe the next one is here, third one, fourth, fifth, and sixth, and maybe one more here. So just assume this is observations we have, and we use the data to draw this on our graph. So what the line we should draw to fit this data? So of course here are many different ways to draw a line. For example, we can draw a line like this, but of course we can see this most of the data is above our line, right? So this means this line is not best fit our data. And then we can also draw a line like this, but this seems like too high. And then, so here what we do is we can draw a line, it looks like this. So this one looks a good one. So it looks like a good line to feed our data. But this is what we do is by visualization, right? So visualization cannot give us a very accurate result, because if by the visualization this black line looks a good one, but if we draw another one, this can looks also a good one. So for example, the green one. So we will know this green one, and so we can say this green one and black one is not exactly same, but we can say they are also a good one. So what should we do is we should use some mathematics, some quantify method to measure about what is a good line. So here when we want to this line is best fit, of course there are many ways to measure what is best fit. So for example, we can minimize the distance error. So what this means? This means we can check about the distance between this each point and our line. So if we use this green color here for the first, the lowest one data, so the distance is about this one, the green here. And then for the second is from this point to the line. The third one is very short distance. And then the next one, this is a little far away from our line. And also we compute all of the difference here. And then we can sum up all of the difference. And then we try to decide it, our beta 0 and beta 1, which make this error is the smallest one. So here, of course, what is how we can compute this difference? So in fact, this difference is our residuals. So we can compute the sum of our EI here. But of course, this EI is equal to our YI minus the beta 0 plus beta 1 XI. But this number can be a negative number and it can also be a positive one. So if we want to sum up this, we don't want to the negative part and positive part cancel each other, right? So what we should do is we should take a square of this one. So make sure all about this distance is a positive value. So then to sum up all of the distance error, then this will become sum up the square of the all residue here. So this is how we can quantify this distance. So when we want to after we minimize this sum of square of our residual, then we can decide the value of our beta 0 and beta 1. So this is an estimator of our beta 0 and beta 1. So based on our definition, this is called as the least square estimation. And then we denote this by the beta 0 hat and beta 1 hat. And also we use LSE for short. Then how about this when we plug in our beta 0 hat, beta 1 hat, and our one observation of our x, we can compute get an equation of y equal this beta 0 hat plus beta 1 hat x, right? So then this line we also call it the least square regression line. So this is the idea about how we can decide our beta 0 and beta 1 to construct empirical data or empirical model from our observations of data. So this is the idea, and then how we can find the beta 0 and beta 1. The idea is how we can minimize our sum of the square of our residue. So this is go back to the calculus, right? So in calculus, we already know how we can compute a minimum of one function. And here for our function, this is sum of a square of an equation. So the idea of this is use the Lagrange methods. So we should compute the derivative of our function and decide this derivative equals 0. And then we can find the value of our variable. And then this variable is the position we can find the minimum or maximum. So the idea of this is same here, how we can find the value of our beta 0 and beta 1. So here, because we have two variables, the beta 0 and beta 1, so what we should do is the first step is we should have two derivatives. The first one is a derivative with respect to our beta 0. And then the second one is a derivative with respect to our beta 1. So here we denoted our the errors as our capital L. And then after we compute these two derivatives, what we should do is we should set these two derivatives equal 0, right? And now we have two equations with two variables. And when we solving this equation, we will get a solution, or say the formula of our beta 0 and beta 1. So here what I do is, of course, I will skip the process about how we can compute this one. So if you're interested in the process, you can just leave a comment at this video, and maybe later I will upload a video about the computing process. But here I just directly give you the equation about the formula of our beta 0 hat and beta 1 hat. So the equation is look like this. So here this is looks a little complicated, but the idea is if we look at this two equation, for the formula beta 1 hat, you can see this in this equation we only need the information about our two pairs of observation xi and yi, and we also need the number n, which means how many pairs of the data we have. But then for the compute our beta 0 hat, we will accept the value of our xi, yi, and n. We also need the solution of our beta 1 hat. So later, when you use this formula to compute the value of our two variable beta 0 and beta 1, you should first compute beta 1 hat and then compute beta 0 hat. And this equation looks very complicated. But if you remember what the definition of our sample mean, so sample mean is like the sum of our, like for x, sample mean of x is sum of all the value of xi and then divided by n. So here, based on the definition of our sample mean, in fact, we can rewrite this formula much simple. So here we can see the equation will become this part. We still compute beta 1 hat first, and then compute the beta 0 hat. Okay, so this equation we can rewrite as this one. But again, so here in the equation of our beta 1 hat, it still have some part looks complicated. So if we denoted the complicated part term as this one, so we use sx sub xy to denote the part in the numerator of our beta 1 hat, and then we use the term of sxx to denote the denominator of our beta 1 hat. So we can rewrite our formula like. So now this equation looks much simple than before. Okay, so this is a formula how we can decide the value of our beta 0 and beta 1 to construct an empirical model based on our data. So here let's look at one example. So this example is find the linear square regression line for our data. And here if we look at our data, we can see we have 5 pairs of the observation. So they are the xy equal 1, 4, and 2, 3, and 4, 1, 6, 2, and 8, 0. So here for the regression, the pairs of the data is very important. So that means if here our x is equal 1, then we should use the data y equal 4. Right, it will always be the pair of them. So then here the question is ask us to find what is the linear square, the least square regression line. So that means, in other words, we should find the value of our beta 0 and beta 1. So we already have the formula of our beta 0 and beta 1. So that means to use this formula, we need to first compute so many important part here. So for example, we need to compute about this x bar here. We need to compute y bar, the sample mean, to compute the sub xy and s sub xx, we need to compute here about the sum of xi times yi, and also about the sum of the si square, right? So here are so many parts we need to compute. So because of this, before we use the formula, we should first compute each of them. So when we do this by hand, what we should do is, in fact, we should always have the several more column here. So for example, the first column is about x squared, and then about y squared, and then the last one is about xy. So based on this one, for the column of the x squared, of course, this is each of the value of our x take square. So for the first one, when x is equal 1, we will compute that 1 square will equal still 1. And then for the next one, about the 2, when x equal 2, we will compute 2 square equal 4. And the next is when x equal 4, the 4 square equals 16. When x equal 6, we will compute the square of this is 36. And when x equal 8, we will compute this is equal 64. So this is for our first column. And then the next thing is, how about our y square? So this is similar, we will compute this. So for the first one, when y is here, when y is equal 4, we compute this is square equal 16. And then we will compute all this one by one. So we will get our next column, the y square column. And then the last column is about our x times y, right? So x times y is, we also do this by the pair of our value of x, y. So that's why we will get the first is 4, and then 6, and then 4, and then 12, and then last one is 0. So now we get the value we need for each column. So if you look at my table for data, you can find here, after each of the pair of the data, I still have one row here. So what this means, this is a row I want to compute the sum. So this, for each column, I will compute the sum. So for the first column, about our x, the sum is all of the sum of our value x. So the answer of this one by calculator is 21. And for next, about the y is 10. Next is 121. And for the y square is 30. And the last one is 26. So now what we have is we get the sum of each column. So after we have this one, to plug in the value into our formula. So what we need in our formula, we need the x bar, we need the y bar, right? The sample mean for our x and sample mean for y. So now this x bar and the y bar, so this in fact is equal the sum of our x and divided by how many number we have for our observation. So here we already have the sum of our x1, so this is 21. And in total, we have 5 pairs of the data. So that's why this x bar is equal 4.2. And then similar for our y bar. So we will get the answer for this one. So this is for our y bar. So that's why we will have y bar is equal to. And then in our formula, we also need the s sub xy and s sub xx. So for the s sub xy, we will use the sum of our last column. So this is 26 minus the number of observations, so it's 5. times the value of x bar and the value of our y bar. So the answer for our s sub xy is negative 16. And then similarly, we can compute the value for our s sub xx. So we'll get 32.8 for our s sub xx. So now we already have all the parameters, all the values term we need for our formula. So now we can first compute our beta 1 hat and then our beta 0 hat. So here the beta 1 hat will equal s sub xy divided by s sub xx. So that's why here we will have the answer of this one is negative 0.49. And then use this value of our beta 1 hat, we can compute our beta 0 hat. So it's 4.05. So now we get the value of our beta 0 and beta 1. So that's mean we finish the process of construct our empirical model. So our linear least square regression line is our 4.05 minus 0.49x. So this is our least square regression line. So before the end of the video, I want to talk a little more about the residuals. So we already know the method we compute our beta 0 and beta 1 to minimum the sum of the square of our residuals. And now after we construct this least square regression line, so we can compute our beta hat based on the value we have about xi and our beta 0 hat and beta 1 hat. So in other words, we can have our equation of our EI like this. So here, what's the name of this yi? So yi here is the actual value of our data. And this yi hat is the expect point based on our least square regression line. So please remember when we introduced, in last video, when we introduced an empirical video, we said for the error term, we have some assumption of them, right? So we said this can be have a mean of this error term should equal 0. And also here, if we have some more assumption about this, we can assume this our error is a random, right? We call it a random noise. So random means our epsilon I, the error term, have uncorrelated between each other. Or in other words, if we compute the covariance of our epsilon term, the error term, it should be always equal 0 for any I and j. And here we still have one more assumption about this. So the mean of this error term is equal 0. And here we can assume the variance of our error term should equal sigma square. So here this sigma square is a constant. And this is for any I of our error term, it should be equal each other. So here, let's give a quick summary about this. So for our error term, we have the mean of our error term is 0. And then for our error term, the epsilon I, in fact, this one is uncorrelated with each other. But the variance is always same. It's always denoted by a sigma square. So then the next thing we can talk about is how we can estimate this value of our sigma. So here we can in fact have one unbiased estimator of our sigma square. So we denote this by sigma square hat has this formula. So this is equal our SS sub E divided by n minus 2. So here the equation of our SSE in fact is the sum of the square of our residual. So this is an equation for our SSE, and this is an unbiased estimator of our sigma square. So here extent of this SSE, in fact, we have two more equations here. One is about the SST. So here the SST is about the difference of our y. So this is the sum of the y square minus n times the square of our sample mean of y. And then SSR is a term about the beta 1 height times our S sub xy. So based on the definition of these three terms, the SSE, SST, and SSR, we can have the relationship of these three terms as SSE is the difference between our SST and our SSR. Okay, so this is about the equation. And then if we use the data of our previous example, so here this example is we want to compute the estimator of our beta square. So of course what we need to do is we just use the formula of our unbiased estimator of our sigma square, right? So this is our SSE divided by n minus 2. So here what we need to do is, of course, we have two methods to do this. The first one is we can compute the sum of the square of our errors here, right? So if we want to compute this one, then what we need to do is based on our value of the beta 0 hat, beta 1 hat, and all of the xi, we need to compute all of the yi hat. And then after we get this value of yi hat, then we can sum up the square of the difference between yi and yi hat. But this is also another way we can do this. The other way is we use the relationship between our SST and SSR and SSE. So that means because SSE is equal double ST minus double SR, so we know this will equal the equation of our 1 over 5 minus 2. This is our denominator, and for numerator this is about the sum of our yi square minus the n times the sample mean of our y square minus the value of our beta 1 and S sub xy. So based on this one, because the S sub xy is be computed in our previous question, so this one we will have less computing of the compared to the other formula, right? So now we only need to plug in the answer from our previous table. So here, if you want, you can go back to the previous video about this table. So we have the first term equal the 30, and then the second term become 5 times the square of 2 minus the value of our beta 1 height is negative 0.49, and the S sub xy is value negative 16. So now we use a calculator about this term, and we will get this final answer of our estimator of sigma square is 0.72. So this is how we can compute our estimator of the variance of our residue. So this is the end of our video, and please subscribe my channel, and you will get notification if you click on the bell when I post a new video. So in my next video, we will continue talk about the linear regression. So see you in my next video.